Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Frank Marchis. I'm a senior researcher at the SETI Institute and Chief Scientific Officer at Unistellar. So today we are going to talk about SETI search for technosignatures specifically, and for this I invited Vishal Gajjar. Hi Vishal, how are you?
Hey Frank, thanks for having me. Excited to talk to you about our latest work.
Thank you for being with us. So we are going to talk about a new project, a groundbreaking mission to uncover periodic signals emanating from the core of the Milky Way, and the project is called Breakthrough Listen Investigation for Periodic Spectral Signals, or BLIPS in short. And the paper was published recently in Astronomical Journal. The title of the paper is a 4.8 gigahertz galactic center search for periodic technosignatures. And Vishal is the lead of this project and one of the co-author of this project. So Vishal, let's go straight to the point. You're a SETI Institute astronomer. You search for aliens, search for technosignatures, and for that you are leading the BLIPS project. So what is BLIPS?
Yeah, thanks, Frank. I guess in SETI, what we do is that we are actually searching for various signs of advanced technology. And in radio SETI, we are searching for various different kinds of signal, but we mainly try and search for this one particular class of signal, which we call a narrowband signal that puts lots and lots of its energy into just very few frequency channels or just very few hertz. What we have been developing over the past few years, and which we recently kind of demonstrated with this new technique, is that there are other classes of signals as well, which are equally important, and they should be searched alongside we search for these narrowband signal. And this additional class of signal are just simple periodic signal. So we know nature does not produce spectrally bound. So what I mean by that nature does not produce signal that are limited to only a small range of frequency and pulsating.
Yeah.
So if you do detect a signal like that, that's a very good sign that they are engineered signal. And blips is a tool that we develop to search for them.
So you are searching for what you call in the paper a train of pulses, right?
Yes,
So that will be basically a signal which is a specific frequency and repeat itself.
correct.
Okay. Uh, so why aliens civilization will use that to tell us that they are here?
Could be multiple reasons for us detecting them from aliens. First is that they could be deliberately transmitted by them to draw our attention. These are what we call beacons. Then other are what we call leakage radiation. So if I can share my slide, I can show you we routinely produce signals like this. For example, our air traffic radar signals. So imagine that you are sitting somewhere near the airport. You might have seen a rotating antennas. So these
Mhm.
antennas, what they do is that they produce powerful pulses, and this is how they monitor activities in their sky. These signals are quite bright, but it's just to kind of demonstrate the point. Although we don't have a sensitivity to detect these kind of signals from too many sources, but let's just take this as an example. This is a radio signal that we generate and we produce quite a lot. And they don't really stop at the aircraft. They keep traveling in space. So if there are intelligent civilization out there looking at the Earth, they will detect signal like these because this signal might be uh, coming. I mean, this signal, for example, are already originating from large number of sources on Earth. And our goal is that there are similar Earth kind of planets out there. If there are more such civilization, intelligent life out there, using a radio for their own purposes, their leakage radiation can also travel in space. So similar to like as Earth is one of the small fraction of our Milky Way galaxy. There are billions of other sort of Earth-like planets or life forms out there, and we are hoping that maybe one of them might be using radio for their own communication, and these can leak out in space, which by sitting here on Earth, we could detect them. So the entire purpose of our program is that this is an exploration. We don't know if ETI is actually broadcasting these,
Yeah.
but we have a hypothesis that these are the most easiest signal to produce, So even if they're produced intentionally or non-intentionally, we need to have tool set to detect it. And this is the first time that we had developed such a tool set to detect such signals.
Interesting. Let's go before I go back to this first time. We have people joining us from New Jersey, USA, from Yorkton, Australia, Valdivia, Chile, hola, Portugal, Ireland, Denmark, oh, Chaclacayo in Peru, Birkenhead in England, Berlin, and more in Minnesota, in Vancouver, in Delaware, in Portugal, in Norway, in Italy. A lot of people joining us from various parts of the world. Hello, we are talking about the BLIPS project, a project to detect periodic signals that could be coming from uh, extraterrestrial civilization. And for that, we invited Vishal Gajjar to talk, the PI of the project. So something that very surprised me is and when you say that this is the first time we've done that, so that means that before we were not looking for periodic signals specifically, or we're not looking in this direction. What do you mean by that?
Right. So these signals are quite hard to detect. Our standard technique, which we have developed to detect narrowband signals, does not necessarily detect these kind of signals. So we were not looking for them. And I was very fortunate that I found a graduate student who was very interested. His name is Akshay Suresh. And I would like to give shout out to Akshay as well, because he basically developed the entire tool that we have deployed for these searches. So these signals have been proposed over many years theoretically, but nobody had kind of went ahead and searched for them. So these are the first time that we made an active effort in order to expand our parameter space of kind of signal research, and then we went after this one particular class of signal. We are hoping this is just the beginning. This is going to open up a new kind of parameter space, and we are hoping that by with this, we will be able to explore other classes of similar signal that we have not searched before.
Excellent. We have people joining us from more places. You're very popular. We have people from Greece, Italy, Pennsylvania, Michigan, Kosovo, and the Orion Belt. I think that's a joke. Okay, so these students been working with you in developing the algorithm, right? Where the data is coming from? Where coming from?
Right. So if I can share my slides again, the signal that we have currently searching for are actually coming from just one direction. So let me recap what exactly we are looking for. So we are looking for alien transmitter. This is just an artist's impression of like what an alien transmitter might look like. You can imagine it to have like a multiple beams rotating in sky, similar to the radar that we have on Earth, but obviously on much larger scale. If you have objects or transmitters like these in space and they are rotating, they are producing these similar kind of pulses that we are looking for. Now think of them that these are located somewhere in the galaxy. So what we did is that we carried out a detailed search towards the galactic center. Now you may ask why towards the galactic center. So the reason for that is that compared to any different directions in the sky, if you look towards the galactic center, as you can see in the image, you are most likely to encounter the largest number of stars that you can ever encounter towards any direction in the sky, because that's where the galactic center is located. And as we know, galactic center of our Milky Way galaxy contains billions and billions of stars. So if you look towards that direction, you have a high chance of looking at a large number of stars and potential planet that we might not even be able to see in any other direction. So that's why, in order to kind of have the best chance of success, we went towards the direction where we had the largest number of stars that we can see in one particular pointing. And in order to search, we actually use a telescope which is situated here in the US called the Green Bank Telescope in West Virginia.
Mm-hmm.
So the Green Bank Telescope is actually 100-meter in diameter. It's one of the world's largest steerable radio antenna. It has the capacity to operate starting from all the way like 1 gigahertz to as high as like 100 gigahertz. So it has excellent frequency coverage. it is super sensitive. And as a part of the Breakthrough Listen program, we actually have 20% of the time on this telescope dedicated exclusively to search for this kind of technosignature. So Breakthrough Listen has been quite successfully utilizing this telescope to cover large area of the sky and large area of the frequency. And as a part of the Breakthrough Listen project, we also survey the galactic center to search for this one particular these classes of signal.
All right. Um, there is one thing interesting as well is that when you look at the galactic center, you see a lot of stars, but you see also older star which had formed a long time ago, or sometimes the third generation of stars. So it means that if there is a advanced civilization, is most likely to see them in the center of the Milky Way than in the outskirts of the Milky Way.
That is absolutely true. That was one of the other reasons why we looked at the galactic center. Is not just the sheer number of stars, but the timeline the Milky Way that these stars had in order to develop intelligent life. As we know, on Earth, it took a long time to develop intelligent life, and we can kind of expect the similar time scale at other places as well. So, as older the stars are, you are more likely to find intelligent life. Moreover, the other reason we argue is that the galactic center is, in some sense, a Schelling point. So, in game theory, if, for example, if the two parties are unaware of what is the unaware about the channel of communication, they can come up with what is the most common thing that they both know about. So,
Mhm.
let's take this example and now think about from ET and our perspective. Let's say ET are actively trying to get our attention. Now, they can put the transmitter anywhere in the galaxy, correct? Now, it is likely that we may be looking towards the direction, we may not look towards that direction, we might miss it. But if they place the transmitter exactly at the galactic center, that increases the chances that anybody else in the other part of the galaxy would certainly know about that one place. And they would certainly do extensive surveys for various different scientific purposes, and they are most likely to find it. So, if the purpose is to be detectable, then placing a transmitter near the galactic center increases the chances of that. And
Ah,
that is why we expect that looking at the galactic center, obviously, the reason that you also alluded is this large number of sort of older star, as well as that galactic center is a Schelling point, again emphasizes that we should be looking at the galactic center with extensive survey. And that's why uh, the program that I'm leading searches from 1 to 100 gigahertz of the galactic center for the science of intelligent life.
thank you. We can stop sharing the screen so we can see Vishal, please. Thank you. Okay, so a lot of people asked the questions already. You've been reading my notes, guys. So, what did you find? And this is a question we got from two people, Pete Piero and Phil Marthlu. Uh, did you find anything?
Unfortunately, not. Otherwise, it would have been a huge discovery. Um we did not detect any signal, but that is not that is something not to feel disheartened about, because, as I mentioned earlier, this is our first attempt to look for these kind of signals. We have never searched for this kind of signal, and this is the first time we are like this is our we are kind of like babies taking our first steps. We have not yet started walking, and forget about running. So this is just the beginning, and we feel that even if we have not detected it, we have opened a new parameter space, a new class of signal that over the past 50, 60 years in the history of SETI, people have not searched. So with the newer additional tools, with the newer technique, and with the newer targets that we will have a capacity to now observe, with the number of radio telescopes which are joining our program, we will be able to search for these kind of signal for the first time. So although we didn't find anything, I still don't feel disheartened, and I feel that this is opens a completely new chapter, and I'm quite excited about it.
Yeah, I am too. Philip Dennis, thank you very much for your donation. We are indeed super helps alone and lost among the star, but I don't think we are alone, and that's why I work at the SETI Institute. Vishal, how many stars did you observe with this survey, and how for how long? Just to give us an idea of the survey itself.
Correct. So the entire survey actually captured a very small part of the sky. It is just directly pointing towards the center of our galaxy. And in technical term, it's 4 arc minute by 4 arc minute region. So we actually don't know exact number of stars because there are many stars which are so far away from us that we don't really see them. We
Hmm.
only know about our neighborhood. So, but we can estimate them. So what we know is the density of star and how it changes as you move towards the center of the galaxy. We know that the density increases. So we can model that if you look from Earth location towards the center of the galaxy and you consider the density change as we model and we see in other galaxies, we estimated that we actually must have looked at close to like a 500,000 star, and that's just an enormous number. Typically, in a radio SETI survey, we look at a few thousands of stars, but this is a survey because it's looking directly at the galactic center. We can safely say that this survey actually must have kind of encountered close to 500,000 stars, which is a huge number.
Hmm. And for how long?
So we observe for total 4.5 hours. So this is a small subset of the actual observations that we've been doing of the galactic center. For this one particular paper, we only reported for 4.5 hours. But overall, at this frequency, we have observed for 20 hours or around 25 hours or so. And we have a similar programs going at more higher and higher frequencies of the similar scale.
All right. All right. We have a lot of viewers watching us. So just to let you know, we are going to take questions. So if you have any questions, write them down, and the team at the SETI Institute will send them to me. Um, so in the meantime, Vishal, what's the next step? What's the next step for you research and for this kind of research specifically for the blips
Right.
project itself?
Right. So if I could share my screen again, uh, the next part is that. So let me again reiterate what exactly we did. So what I'm showing you here, just bear with me for a moment for this plot that I'm showing you on the right hand side. So what you are seeing is that this is a frequency on the y-axis and time on the x-axis. So think of this that we are recording from a telescope like this green bank. Every second we observe all of these frequencies together, and then as we progress, the plot kind of moves from your left to right. You see these yellow dots. Now these are the periodic pulses. This is a simulation. This is
Mhm.
not a real. These are not real signal, but this is just a simulation to demonstrate that these are the kind of signal that we have searched. And how do we find them? So we actually apply this quite clever algorithm called fast folding algorithm across all the channels, and that allows us to actually find periodic signals. So what I'm showing you again on the right hand side, it's the same frequency on the y-axis, but now the x-axis it replaced with the period. And what you see, the color there shows the intensity. So you can see that if there is something periodic, we can see that as a bright spot in frequency versus period diagram, and that allows us to detect signals like these. Now what's future? So the future is that we are going to expand the search where the signal doesn't necessarily need to remain fixed at one frequency. And this is quite true that due to motion of the earth and due to maybe the transmitter itself is moving, there is the Doppler drift. So what I showed you earlier on the left-hand side panel, you see that the signal, although it pulsated, but it still remained stationary at the same frequency. But you can also think about the case where signal will no longer remain stationary and it will drift. It will basically change its frequency as the time progresses. So the next step for blips is to search for these kind of signal as well. And that is going to be, again, an interesting aspect of this search because, again, nobody has searched for this kind of signal before.
All right. So, are you going to continue to use the Green Bank telescope for this kind of study, or you expand to new antennas in the future?
So we have a number of radio telescopes that are participating in Breakthrough Listen project. For the Galactic Center survey, we aim to use two radio telescope. One is obviously the Green Bank telescope, and I heard you mention that somebody is from Italy, so they also should feel proud. There is a huge radio telescope in Italy called Sardinia Radio Telescope. which we also actively use to look at the galactic center. So
Mhm.
yes, these are the two primary telescopes which we are aiming to use for our galactic center survey.
Excellent. Okay, we have questions. So one question, is there any black holes at the center of the galaxy? And my question is, will this be a problem for your search?
It will not be a problem. We know there is already that there is a black hole. Is in fact as what we call a supermassive black hole at the galactic center. Uh, we don't feel that is going to be a problem for us. Remember, the time kind of what we are searching for is not the star actually exactly at the galactic center. These are the stars which are in the vicinity of the galactic center, or even in the line of sight from us to the galactic center. So these are the number of stars that are spread all throughout the galaxy, which are basically unaffected by the massive black hole at the center. In fact, this is a good science case. So we have an ancillary science studies that are ongoing on the same data that we have collected for technosignature, where people are searching for pulsars. Because if you find a pulsar rotating around this supermassive black hole at the center of the galaxy, that allows us to kind of understand some of the properties that we have not yet really found out about our supermassive black hole at the center. So, in fact, I would think that it's a good point. It's a
Yeah.
good thing that there is something more. Even there is an exotic astrophysical object out there, and that actually doubles the science output from our observation.
All right, we have a question for Rick Childers. So that's a difficult question because there is calculation, but I'm going to mention it. So we have been broadcasting signals at the speed of light for 125 years. How many potentially habitable systems would have received those signals by now?
I don't think so. I have a clear answer to that because in our proximity to us, there are not too many systems that are we have found to be habitable. Now, I like to kind of and again mention this one point. Definition of life is not. I would not want to kind of make it so much anthropocentric.
Hmm.
Life could be anything that we cannot even imagine. So we don't have to be so much focus on habitable planets or planets inside habitable zone. Life can arise at any location. Even if, for example, we have been looking at Europa in our own solar system. Europa is not inside any kind of habitable zone. If, for example, for in future we find a life, what do we call it? I mean, is because this is not inside a habitable zone, so that is definitely opens up a new possibility, right? That life doesn't need to be inside habitable zone. So it doesn't matter that if we have found exoplanets, if we have not found exoplanet in this nearby system. I think it all matters in how many number of total stars that these signals would have reached. And I would say that is still not a large number. That is still within like a few hundred. I still need to check, but I think that's probably in that order, like only like a few hundred stars, where any kind of radio broadcast that we might have done on our history would have reached to these systems.
Yeah, that was a question by Rick Childers, by the way. So I would like to add something that's in at the SETI Institute. There is some kind of competition between three ways of finding life elsewhere in the universe. Finding life in the solar system by using spacecraft and robots, etc. Finding life on the exoplanets by analyzing the atmosphere of the planet. And then there is SETI. SETI is the search for technology, intelligent technology. And something interesting with SETI is that it doesn't really matter the life, the type of life. It doesn't matter the chemistry. It doesn't matter if those aliens are particles of life floating in the atmosphere of Jupiter-like exoplanets. What matters is that they're trying to communicate and they're trying to emit signals, intelligent signals. And that's the beauty of SETI. It's really truly to find an intelligent signal coming from any type of civilization, any type of life. So
I
that's why I think it's important we continue to do SETI no matter what.
I totally agree. And it also increases the amount of distances that we can search. We can only search in our neighborhood for the, like, for example, you mentioned about solar system. That's the only place we have access to. We can only search for biosignature in our solar neighborhood. But SETI is something that you can do if the signals are powerful enough. You can even detect them if they're coming from other end of the galaxy. So think about the number of target that you basically can search with this thing, and that's why I guess I agree. SETI is so special in that sense that we have such a huge, we have this new technology that we allowing us to kind of explore the entire universe to find life.
Yeah. Okay, Vishal, last question I have for you. So where are you calling me from, first of all? Where are you located right now?
I am at the heart where SETI happens. I am at the Hat Creek Radio Observatory, the
Okay.
Allen Telescope Array, the only facility in the world which is dedicated for doing SETI 24/7.
All right. So what's the next step for you in your career? What do you think what's gonna we're gonna hear about in the next 10 years from your work?
I would continue to kind of explore this particular parameter space of exploring different search for different kinds of signal, because I feel that this is the real time where we have the right tools. I didn't get time to go into the details about AI and machine learning that we have deployed and we've been using. That is certainly kind of expanding this parameter space of searching for different kinds of signal, like looking for anomalies, looking for things, looking for outliers. This is the direction where I am currently focused on, to exploring the parameter space of type of signal and kind of completely be agnostic and just finding any kind of anomalous signal that we can look for. And that AI is actually going to allow us to do that.
All right. So guys, remember this name, Vishal Gajjar. It's possible that in 10 years you will hear that Vishal and his machine learning algorithm, have discovered life in our galaxy. So thank you very much, Vishal, for sharing your exciting research in the field of SETI. I'm very glad we have the opportunity to talk again. And come back when we have more news and more instruments or more results with SETI, maybe to tell us when we find the signals, of course. Thank you very much again.
Thank you, Frank.
Okay, everybody. So that was the SETI Live with Vishal Gajjar. We talk about the blips. We are the SETI Institute, the Search for Extraterrestrial Intelligence Institute, located in Mountain View, California, in the heart of the Silicon Valley. Uh, we are a non-profit organization, and our goal is to find life, any type of life in the universe. You can be part of this great adventure by simply watching those videos, liking them, making comments, sharing them, and telling people what you think about the SETI Institute, following us on social media. We are on every platform, I think, right now, even the new one, Threads. So you will hear about us over there as well. Um, you can also visit our website at seti.org and join our e-news by clicking on this link written connect.seti.org/sign up. We have basically a newsletter being published every week where you can hear about recent result and activity at the SETI Institute. And finally, if you're inclined, you can make also a small donation to support this program. This is the communication team. We have a SETI Live every week, and several of us spend some time, researcher at the SETI Institute and other places, spend some time talking about the excitement of astronomy and space exploration and astrobiology as well. Next week, we will talk about instrument. We talk about a new instrument that could be extremely useful to image and detect exoplanet by providing an angular resolution, which is a quarter of the theoretical resolution of a telescope. This instrument is called FIRST. It's a very technical thing, but we hope to have the opportunity to explain to you why this instrument is important for the search for exoplanets. In the meantime, enjoy your weekend and see you next week for a new SETI Live. Thank you again, Vishal. Bye-bye.